Hello, guys. Welcome to another episode of Cuda Education. Today we have a lot to cover, so let us get into it. So we are still on the compute headless script. We're still on the compute headless script, and we are basically, doing a compute only application on um, we're doing a compute only application. So pretty much we're just adding we input a bunch of numbers which is largely irrelevant, but we're basically just adding series of numbers, right? So we start at zero, and then the next number is one, and then after that we just add the two previous numbers to get the next number. So 0 plus 1 is 1. And then when we move, um, 1 plus 1 is 2. And then when we move, 2 plus 1 is 3. And then when we move, 3 plus 2 is 5. And then when we move, 5 plus 3 is 8. And then we move, 8 plus 5 is 13, and so on, right? So we have, it's just a simple computational thing. We transfer a bunch of numbers to the GPU from the CPU. We do a calculation. I mean, for our intents and purposes today, we don't particularly care about the calculation. So we do a bunch of calculations. We get results from the calculations on the GPU, and then we send it back to the CPU for it to be displayed on the screen as we see here. So the numbers are being displayed on the screen here. Hopefully you guys can see it properly. Um, I have to work out something for the short, so I apologize if it's a little bit small for the YouTube Shorts videos, but it's a work in progress. Anyway, guys, so we're basically adding a bunch of numbers on GPU, and when we're sending it back to the CPU. So CPU sends a bunch of numbers to the GPU. GPU adds a bunch of numbers. The GPU sends the results back to the CPU. The CPU displays those numbers. Okay. We did this in the previous episode. Okay. Um, so what I wanted to focus on is that and I'll zoom in just to make it readable for you guys. Um, right. So let us focus on what I want to focus on today is the section that talks about memory types. Okay, so here we're dealing with memory types for choosing the correct memory for our application. Okay, so we need to choose the correct memory for our application, and this is pretty much where I want to spend this episode on. Now, notice that this memory type discussion is part of the create buffer function. Okay, so we're creating a buffer to basically choose the correct memory type, um, because that fits the properties of the buffer, right? So what are the properties of the buffer? Um, we want to choose a memory type that fits the properties of the buffer. So this create buffer function has memory property flags. Okay, so notice the signature for the create buffer function. We have usage flags, memory property flags, the buffer itself, memory, all of that good stuff, right? But the memory property flags, okay? So here in this for loop, we're cycling through all of the memory types on our system to find the right one. All right. So this is just defining the actual create buffer function, right? And this is where we cycle through the various memory types that we have accessible to Vulkan, and we choose one of them. But let us just look at where the create buffer is being called, right? So we do create buffer, right? So where is it being called? Okay, it's being called here, right? So notice that we want a transfer related stuff, and we want VK memory property host visible. Okay, so we want it to be host visible. So basically CPU related stuff, right? So that's one place that we use the create input data to VRAM using a staging buffer. Okay, but we have some host visible memory here that we're creating a buffer for that. Let's see the second place that we call create buffer. So we call create buffer here again. We have usage storage bit, usage transfer related stuff, source and destination. Okay, source and destination are also for this guy. So we have storage buffer stuff, source and destination, and then the actual flag is VK memory property device local bit. So this is now GPU memory that we're dealing with, right? So here we have CPU memory, here we have GPU memory, and we have to copy, do the staging buffer stuff to get from one CPU side into GPU side, okay? And we do a bunch of stuff in order to do that. But that's not what I want to focus on today. So let's go back to um, the task at hand. Okay, so we're talking about the create buffer function. Notice that we had the usage flags and then the memory property flags, right? So the usage flags is just like, how we plan on using it, and then the memory property is actual memory properties that we actually need from the memory, okay? Usage and properties, two different things. There's a usage side, what are we using it for, and then the actual properties for the memory that we are using for our the memory that we're using for our application. All right. So we basically do a for loop, and we loop through all of the property, all of the memory types that are available to us, and then when we find one, when we find one that matches what we need. So notice that this if statement here, so it's property type, property flags, right? Device memory properties, memory type, property flags, and memory property flags, right? So equals memory property flag. So if this statement is true, then we get what we want, and then we assign that memory type, and memory type found equals true, and then we break out of the for loop because now we have found what we wanted to, and we get what we want. Okay, we don't need to loop anymore because we've found what we wanted to, right? Um, Notice that it's this memory property flags it's matching up against, right? So it's matching up against the memory property flags, and it's saying if this AND statement is true and it equals the memory property flags, then we have found it. We memorize what the memory index is, and then we break out of the loop, and then we proceed as we need to, right? I just want to focus on sort of this conversation right here. Okay. I'm not getting into the staging buffer. I'm not getting into moving from CPU to GPU or anything necessarily like for this application. What I want to focus on is, and I'm simply just adding, I'm adding some, functionality to the code, because what I want to focus on is that when we run the application, um, I have to actually close it out. Okay, yeah, I had it running before, so when it does that, it gives me a build error. Okay, so what I want to focus on is simply the property types available on our system, right? So we need to have a conversation on the memory types and the memory heaps that are on our system. Okay, this is an important conversation. I'm not even going to do anything talking about particularly focused on the application. Um, we're just going to talk about what is available on the GPU. Okay, so I have an NVIDIA GeForce RTX 4050 laptop GPU. Okay, now um, there's a thing called Vulkan memory heaps and Vulkan memory types. All right, and we need to fully understand what's going on here. Uh, First of all, this is this the memory heaps is actually it's like what everything derives from. It is the original, it is what starts the conversation. Memory types is largely tangential. What do I mean by that? Memory heaps is the actual physical memory that you have on your system. So the chips that you have in your laptop, the chips that you have in your desktop, in your GPU, the physical memory, the living physical memory that the chips and all of the physical tangible stuff that you have, that's what the memory heap is. So on my system, for example, I have VRAM, right? So it's a device local heap, VRAM for our purposes today and what we're trying to cover. You could basically think of VRAM as the GPU memory. So you can't I know there's been discussion online and stuff about different GPUs and how much VRAM it has, and this has so much VRAM and blah blah blah. And the entry level card has less VRAM, and the more expensive card has more VRAM. And why did Nvidia and XYZ change up the amount of VRAM and blah blah blah? And you're spending more for less VRAM in the new generation and blah blah blah, etc. etc. For our intents and purposes, the VRAM is the GPU memory that we have to play with, right? Um, I'm gonna assume that I guess my total VRAM is about 6 or 12. I don't know, right? But as far as Vulkan is concerned, in its purposes, we have Vulkan has access to 6 gigabytes basically of 5,921 megabytes of VRAM on my system. Okay? So that is physical memory in my laptop. Okay? Physical memory in my laptop. Now, heap 1, so that's heap 0. Heap 0 is the VRAM on the GPU, device local. Heap 1 is system RAM on my laptop. So this doesn't have anything to do with the GPU at all. This is just system RAM that generally the CPU has easy access to, and it's system RAM, right? You guys know system RAM. Obviously, the more system RAM you have, the better your system runs, the faster your operating system is. You could open up a bunch of tabs on your browser, and you will still be okay. The system is not going to bog down because you have enough system RAM. Now, if you don't have enough system RAM, then you get into problems because now you have memory constraints, and I don't know, maybe you get into virtual memory and you're using, you know, In the olden days, you would try and use the spinning hard disk as RAM, and that would just slow your computer even more because that RAM is just very slow. Anyway, so for Vulkan's intents and purposes, you have or I have 8,043 megabytes of system RAM. Okay. Now, this is just a slice of the total system RAM that I have on my system because, of course, we have to run the operating system. We have to run drivers. There's overhead. We have to make sure that your cute wallpaper picture is showing on your desktop and all that good stuff, right? So Vulkan only gets a portion of the total available system RAM, right? And this is the window that it has. Okay. Now, all other conversations proceed from this physical memory that we have on our system. Okay. And really and truly, there's really only two physical memories um, there. There's only two physical memories. So you could have 10,000 types of memory, but as far as the physical memory, it's only two physical memories that are there, right? So this is just like right, the memory heap is just like set in stone, concrete, tangible memory. When you start getting into Vulkan memory types, right? Vulkan memory types is just a labeling exercise. It's a labeling and a restriction exercise. Okay? So, um, notice that for each one of these types, okay, so we have a memory type of 0, we have a memory type of 1, we have a memory type of 2, we have a memory type of 3, we have a memory type of 4. Okay? But notice that each one of these types, okay, they do have a different tag, a different name. So you have type 0 is none. You have type 1 is device local, which is like GPU stuff. Then you have type 2, which is host visible, host coherent. So that is CPU host visible means CPU available or accessible. Host coherent means that the GPU the is able to access the memory. Okay. Type 3 is host visible, host coherent, host cached, which means that host visible means it's CPU accessible. Host coherent means it's GPU accessible. Host cached means that you are able to cache the memory. So basically, you're able to like save stuff and like instead of checking the variable or the values or the data again, you basically just read what was cached, right? And the idea is that it's more efficient, right? Um, but there are drawbacks to this type, okay? And then you have type 4, which is device local, host visible. So device local means that it's local to the GPU. Host visible means the CPU can access it, and I guess host coherent, which means that both the CPU and GPU can access it. Okay, but like, I mean, we'll get into that in a little bit. But what I'm trying to tell you is that these are just like types of access. These are just labels, right? And we know this because each one of these types is either heap 1 or heap 0. Either it's accessing or it's based on VRAM, which is GPU memory, or it's based on system RAM, which is CPU RAM, right? CPU memory. Okay? But notice that even though, so for example, you have for type 2 and type 3, they're both on heap 1, which is a GPU local stuff, right? But notice that the restrictions on them might be different. So, for example, on type 2, you don't have caching capabilities, but on type 3, you do have caching capabilities. But it's the same physical memory. But as far as Vulkan is concerned, you are placing restrictions on what you can do with it, how you can do it, what are some options you have, etc., etc. Again, we could look at type 4 and type 1. So type 1 is exclusively GPU access only, right? Still heap 0, but GPU access only. So no, the CPU can't access it. Um, it's not host visible. It's not host coherent. There's no caching, I don't believe, right? There's no caching. It's just GPU memory. So that's type 1, but it's still on heap 0. Type 4 still on heap 0, but now it's GPU memory, but the CPU can access it, and you also have this host coherent thing, right? So what I'm trying to say is that the memory types is just Vulkan. It's just Vulkan methodology, and it's Vulkan sanity checks. Generally speaking, in programming, you want to put restrictions on who can access what, who can read what, who can write what, and what are the possibilities. And the reason for that is because you don't want any technology oversight. You don't want unexpected behavior or things that in the background that are happening that you didn't want or think to happen, right? So you put these restrictions on, but on top of on top of the physical memory that's available on your system. For example, there's a highway. The highway is a highway. It's you know it's freely available. You could drive on the highway. Um, but the government puts restrictions on, and even though you could go as fast as your car can go, the government puts restrictions on how fast you could go on the highway. And if you break how fast you could go, there are consequences and repercussions and all of that, right? But the speed limit is a superficial limit, right? The government puts restrictions on how fast you could go, right? Um, so that's sort of a superficial thing. Now the highway is open road, and technically you could go as fast as your heart desires, right? Um, but government puts a superficial restraint on how fast you could go. You could also knock it another way. The highway is a highway, but the manufacturer of the car that you're driving puts a restriction on how fast you could go on the highway. So if your car can only go 120 miles an hour, it could only go 120 miles an hour, and that's a limit, a superficial limit that is placed on you as an individual because the machine that you're driving can only go that fast, right? It's sort of a superficial limit. There is no physical thing on the highway, physical feature of the highway that says you could only go 120 miles an hour. It is a superficial restraint that is placed upon you, um, just based on the manufacturer and maybe rules that the manufacturer of the car has to follow and all of that stuff, right? Um, but similarly, you have physical memory, right? Device, device, device local and system RAM, but then you sort of put restraints on how this memory is partitioned and dealt with, right? Again, notice that we have four different types, but literally we have two different heaps. We have two different physical memory. We have four different memory types, but only two different heaps or two different physical memories on our system, right? But Vulkan, in order to have some level of sanity, it puts these superficial restrictions um, on on what you can do, and that's really what I wanted to get to today. So an important conversation to have, and basically this is what this create buffer conversation is trying to figure out. So it's looping through all of the different memory types because it needs to find one that does whatever the memory property flag has in store for it. Does it test for usage too? Um, I guess usage is just, a restriction. I mean, it's a superficial restriction, right? So usage is like, yeah, okay. So so we have so these are the usage stuff: transfer source and transfer destination. But then host visible is a hardline property flag that we need for this one. So again, we have transfer source and transfer bit for this one, but we also have this storage buffer bit, usage storage buffer bit, which I'm not going to get into right now, but you could look that up. So storage, that's also a usage restriction, and then the main thing, it has to be the device local bit. Okay, so we know that for this one, um, it either has to be type 1 or type 4, right? It has to be type 1 or type 4, because we are, we're dealing with device local stuff, right? So it has to be type 1 or type 4. For this one, host visible bit, um, we know it has to be either type. It can be type 2, 3, or 4. Okay. So we know that in another episode we'll actually see which one was actually chosen, right? But I don't want to get into that right now, right? So just based on the overall situation of memory that's on our system, these are tangible chips and tangible memory on our system, and then these are the superficial memory types that Vulkan, you could even say, invents, right? Um, and remember too, like, Vulkan wants to know what you plan on doing with this memory, right? So when you say you want to transfer source and transfer destination kind of usage, Vulkan is going to make optimizations, right? So it's going to be like, okay, we're going to partition off this memory and we only need it for these things. So, we're not going to run XYZ process and take a bunch of luggage and overhead with us because, we're only doing this. It's like going to travel to a destination for like one day. Like, you're gonna go early in the morning. The first flight out, you're gonna go in the morning, and the last flight out, you're gonna come back in the evening or at night. Okay. If you know that you're only going for the day, you're gonna pack very different than if you know you're going for 2 or 3 days or you're going for a week. Right? You're gonna pack different. The optimizations that you're going to do and the approach you're going to take is going to be very different. So if you're going for a week or 2 weeks, you might pay for two baggages, right? If you're only going for the day, you might not even you might just carry a personal item on the flight, right? Maybe you don't, yeah, just a personal item because you're just going for the day, so you don't need a change of clothes or anything like that, right? You're just going for the day, doing what you got to do, and you're coming back the same day, right? Same thing with Vulkan. So these flags are sort of, it's trying to tell you what is it that you're trying to do, and it's going to apply optimization. So these things are superficial. Obviously, there is some restraints, so you know, like heap one stuff generally is gonna have generally is going to have really fast system RAM access, right? Just generally because the memory is based on system RAM, right? And heap zero generally is going to have very fast GPU, GPU access, right? Because it's you're using VRAM to accomplish what you need to do, right? So that is that. I do want to quickly discuss another reality that we have to deal with, and that is how are these let me just okay, so it's we also have to discuss memory paths, okay? So what do I mean by that? When you have something like host coherent, um host coherent, right? Like host visible, host coherent, device local, but also host visible. There's a discussion on how are these things connected. So host coherent basically means both the CPU and the GPU can access the memory. Okay? But then the question is, well, how are you accessing that memory? So if you're on heap 1, which is system RAM, which is CPU RAM, right? But it's also host coherent, which means that the GPU can access it, right? How is the GPU accessing it? What methodology, what bridge are you using to make the GPU have access to that memory? Similarly, if you're on heap 0, which is VRAM, which is GPU RAM, right? But you have GPU RAM, you have heap 0, which is GPU RAM, but you also have it host visible and host coherent. Well, the elephant in the room is, well, how is the CPU accessing this GPU RAM, right? Because this memory type is based on GPU memory, right? So the natural question is, we understand how the GPU is accessing it because it's local to the GPU. We get that, but how is the CPU then accessing that memory? Now, I don't want to get too deep into it, um, but there is okay. So there is pure VRAM, right? So that's GPU only, right? GPU only, and that's it. So it's just pure. So it's just an internal pathway between the GPU itself and its memory, right? It's an internal pathway. Then you have what they call PCIe DMA, right? Um, and this is um, what the staging buffer use. PCIe DMA. It's what the staging buffer use. Um, um, because remember we're transferring over from CPU to GPU, right? So PCIe DMA staging copy it's sort of the methodology that's used to connect the CPU and the GPU memory. Okay, usually you want to use that for like very large files because it's fast transfers, right, and fast access or what have you, right? Um, then you have a thing called bar mapped VRAM. So bar mapped VRAM. Basically, the CPU maps to the VRAM directly, right? So I'm gonna assume that Type 4 is bar mapped VRAM, right? Because the CPU, we know that it's device local memory, but the CPU maps to VRAM directly. So the CPU has access to this memory on the GPU, and that's probably done by bar mapped VRAM. Um, right, that's type 4. Um, so type 4 is bar mapped VRAM, right? So CPU maps VRAM directly, right? We know that type 1 is gonna be just pure VRAM, right? And then yeah, and then there is also system RAM shared with GPU. So system RAM shared with GPU. Um, I believe that's type 2. Host visible, host coherent. So system RAM shared with GPU, right? But the GPU reads, for this one, the GPU reads are slow, right? The GPU reads are very slow. And that makes sense because it's based on CPU RAM, but and it's host coherent, so the GPU has access to it, but it's slow. Um, and yeah, so just to repeat, guys, we have the physical, tangible chips and circuitry on our system, and it's only two types. It's VRAM, heap zero VRAM, GPU local memory, and CPU RAM, which is heap one, and that's local to the CPU system RAM, what we colloquially call system RAM, right? So we literally only have two physical memory types on our system. I mean, two physical memory hardware devices on our system, but as it relates to memory types, Vulkan memory types, then Vulkan goes into its own world and it has extrapolations and it sections off things, and you know what I mean. It's almost like land, right? So you have in Europe you have this big land mass, right? But then we have borders and we section off stuff because we want to create something called countries and different nations and things of that nature. But um, make no mistake, that is a superficial thing that human beings create for themselves, right? So that they have their own territory and all that stuff, right? But as far as the land is concerned, the land is just there. The land doesn't care about any of that. The land is just land, right? But we have superficial labels and things. Similarly with Vulkan memory types, right? So the heaps, I know it says Vulkan memory heaps, but it's just physical. It's just basically memory heaps, right? And then we dice and slice it up as need be to achieve different things. But also notice that these divisions also dictate what kind of access methodology, what they call memory paths. These definitions decide what memory paths are used in order to get to get one to the other. So if you're moving data from CPU to GPU, maybe type 2 would be better than type 4, based on the memory path. Okay. So that's pretty much it, guys. That's our discussion of memory types as it relates to this algorithm. But I did want to go over it because we need to appreciate what is happening here, where we are deciding what memory we're using for our purposes, right? And it's all part of the create buffer function. We have our usage flags and our memory property flags. There are other considerations here, but we just care about what are the properties of the memory, the physical memory, and what do we plan to use it for. And that's pretty much it. Anyway, guys, this is Cuda Education. If you want to be able to run these examples on your machine, you need to get tutorial number 1, which is installing the Vulkan SDK. And you need to get tutorial number 13, which is installing all of these examples. You need to make sure, this is assuming you have a Windows machine, a Windows-based machine with a Vulkan-capable GPU. For this particular example, you do not need ray tracing capabilities. But for the example set that is installed on your system, if you want to run the ray tracing examples, you also need to make sure that your GPU has ray tracing capabilities. For my system, I mean, for NVIDIA graphics cards, it's RTX and above. That will give you Vulkan capability and ray tracing capabilities. For AMD and Intel, I have no idea. But NVIDIA cards give you access to Insight Graphics and Insight Systems, which is tools we regularly use on this channel to figure out what's going on the back end. Graphics debugging and system profiling. Graphics debugging just to see, what's going on and why things crash or what have you. What sort of, what's contained in buffers and different things in the graphics world. And then Insight Systems is profiling. So how fast is your application running, and where is the bottleneck, and why is there a bottleneck, and you know how can we tinker with the code to make sure it doesn't bottleneck. And you get great frames per second. Everyone wants high frames per second, right? We don't want low frames per second. We want high frames per second. Well, in order to generate those frames per second, we have to optimize the algorithm, and that's what Insight System does. Anyway, guys, this is Cuda Education. Thank you for watching. Have a great day.